Greetings and welcome to our group's chemistry video. Let's get ready to dive into our experiments. Safety goggles? Check. Safety gloves? Check. Lab coats? Check. In the lab, make sure to have your long-haired friends tie up their hair so that the strands don't end up falling into a chemical or flame. Covered shoes are also a must because you wouldn't want to have anything toxic poured onto your feet. No sandals here. We should also keep our tables as tidy as possible so that accidental chemical spills and glass breakage can be avoided. Don't leave it to the next person to clean up your mess. All chemicals should never be disposed into the sink. Instead, dispose them in a designated chemical waste bucket. We don't want to get called up by NEA, do we? Last but not least, remember to wash your hands before leaving the lab. Now, we can move on to Lab 1. This experiment involves concepts of stoichiometry through the dilution of various salts by dissolving them in water, just like sugar in coffee. In this experiment, we will need sodium chloride salt, magnesium chloride salt, and copper 2 sulfate pentahydrate salt. First, we need to weigh our desired mass of salt by using the analytical balance and placing the salt into the Petri dish. But wait, how will we know how much salt we actually need? This is where the stoichiometric formulas come into play. Let's take MgCl2 as an example. We can find the number of moles of MgCl2 required by taking its concentration multiplied by its volume. Since we know the molar mass of the salt by adding the molecular masses of elements together, as shown here, the mass required can be calculated by multiplying the molar mass by the number of moles required. Now that we know the required mass, we can proceed on to gathering our salt using the analytical balance. Of course, always remember to wear gloves and safety goggles since these chemicals may cause irritation. As we are approaching the desired mass needed, it is also ideal to close the glass balance door in order to prevent air currents from disturbing the reading. Now, we can move on to dilution. In order to know the volume of deionized water needed to dilute our salt, we need to use the formula M1V1 equals to M2V2. Given the volume required for the diluted solution, as well as the concentrations of both the stock and diluted solution, it can be determined that we need 15 ml of stock solution. Hence, we will need 60 ml of deionized water for dilution. Once obtaining the volume of deionized water needed using a measuring cylinder, dilute the salt by mixing both water and salt together. Some deionized water can also be poured into the Petri dish to catch and dilute any remaining stray salt particles and improve the accuracy of the experiment as shown here. That's a useful tip. Don't forget to stir the mixture until the salt is fully dissolved. This process can be repeated on the NaCl salt and the copper 2 sulfate pentahydrate salt. And there you go, your very own salt solution. Here are the key takeaways from Lab 1. Now, let's move on to Lab 2, acid-base titration. Before we start our experiment, let's rinse our conical flasks and burette. Starting with our conical flask, we can rinse with deionized water in a circular motion as shown here to collect any excess chemical on all sides of the inner flask for disposal. Don't forget your safety gloves and goggles. Moving on to the burette, first rinse with some deionized water provided. We can use a similar motion to thoroughly clean the burette, just like the conical flask as shown here. Then, we can rinse with 5 ml of NaOH provided. We can use a funnel to prevent spillage of chemicals and potential contact onto the human skin. Now, we can start to fill our burette. Fill it up with the standard solution NaOH to just above the 0 ml mark. This is referred to as the standard solution because its molarity is known. Once filled, we can deliver short bursts of solution from the burette tip to expel any air bubbles. From there, refer to the meniscus of the burette to note down the volume of NaOH in the burette as shown here. Then, Using a pipette, add 20 ml of HCl provided into the conical flask. It is referred to as the analyte since its concentration is to be analyzed. We can now add a few drops of phenolphthalein indicator into our 20 ml of HCl solution in the conical flask as shown here. The indicator becomes more purplish pink as the solution becomes more basic, while it turns more colorless as the solution becomes more acidic. Let's see this in action. As you are adding more NaOH and reaching the endpoint, it is advisable to reduce the flow of NaOH to slow drops so that we do not overshoot the volume of NaOH expelled. Remember to swirl the flask as well so that the solution is fully mixed and the endpoint is accurate. The endpoint is reached when one drop of base causes the entire solution to turn pink and the color holds for at least 30 seconds. If the color obtained is too dark, it means that the endpoint has been exceeded and the analysis must be repeated again. We can use a white sheet of paper to correctly visualize the endpoint color. Repeat the process 2 to 3 times to improve the accuracy of the experiment. Let's move on to the calculations. Once again, we need to use the formula M1V1 equals to M2V2. From the titration, we can calculate the molarity of acid HCl as shown. This volume is the amount needed to hit equivalence point. Do note that equivalence is a chemical occurrence, while endpoint is a physical observation. Here are the key takeaways for Lab 2. Let's move on to our last lab, thermochemistry. In this experiment, we will be using calorimetry to demonstrate endothermic and exothermic reactions, as well as determining the enthalpy changes. First, we need to weigh the mass of sodium carbonate and sodium hydrogen carbonate. Weigh the empty falcon tube first so that we can subtract the summed mass of the falcon tube and the salt together. Use a funnel to prevent spillage onto human skin as these chemicals may cause irritation. Here is the mass of both the falcon tube and salt. Now, we can add our salts into the calorimeter. Use a 250 ml beaker for stability when stirring the solution. Also take note of the initial temperature recorded by the mercury thermometer so that we can calculate the change in temperature. A lid is also advisable to prevent any effervescence from making contact with the skin. The sodium hydrogen carbonate reaction shows a decrease in temperature, whereas the sodium carbonate reaction shows an increase in temperature. But what does that imply? Let's take sodium hydrogen carbonate as an example. The formula Q equals to mc delta theta can be used to find the heat change. Since the temperature decreases in the case of sodium hydrogen carbonate, it means that heat is absorbed into the system. Thus, it is an endothermic reaction. To find the enthalpy change, we first need to know the number of moles of sodium hydrogen carbonate used in the experiment by taking its mass divided by its molar mass. Finally, we can use the formula delta H equals to Q divided by N to obtain the calculated enthalpy change. Here are the final takeaways from Lab 3, and we hope that you have enjoyed the video.